Okay, good morning all. Anyone mute yourself and tell me, am I audible or not?
Yes, sir, audible.
Okay, all right. So we will start today's lecture.
Yes, sir.
Uh, in the last lecture, we have seen the difference between power electronics and linear electronics, right? So already we have seen the comparison between power electronics and linear electronics in the last lecture. This two figures I have shown in a last lecture. These are the examples of linear regulated power supply, basically linear electronics and power electronics. It's basically a difference between these two that already we have seen in the last lecture. So I'll just repeat one more point, that is switch mode power supply, and maybe some students have doubt about some explanation about this switch mode power supply. So I'll send you these PPTs with some videos so that you can clear your concept. But still, very uh, small time, we will complete this one and then we will start the second lecture. So in this figure, uh, if you see, there is no line frequency transformer is used, only high frequency transformer which is used here, right? So 230 volt supply directly given to the rectifier circuit. This rectifier is a symbol of rectifier. Then filter capacitor. Okay, so after rectification and after filtering, this signal is given to the primary of this high frequency transformer. But there is one additional coil at the primary side. This coil basically used with this freewheeling diode. It is a protection circuit for this high frequency transformer that I have not mentioned in my last lecture. So I repeat this thing. This particular coil and this diode is basically a protection circuit for. Okay. Uh, so this primary, this particular high frequency transformer and transistor, this in this figure, above figure, that is a linear electronics or linear regulated power supply. This figure in which this transistor is used as a series pass transistor, and normally this transistor used in a active region. But here the transistor is used in a switching, maybe either in saturation or in a cutoff region. So once again, anyone unmute yourself and tell me, am I audible or not? Because there are so many disturbances. Uh, so anyone, am I audible? Anyone, am I audible?
Yes, sir.
Yes,
Hello.
Yes,
sir.
sir.
Okay. It's all right. Uh, so this transistor is used here in a saturation or in cutoff region. So what happens exactly? This DC voltage is given, that is unregulated DC voltage after filtering. This is given to the primary of a transformer, and in which this transistor basically this transistor is on and off with the help of this controller. So whenever this transistor is on, only that time the pulse or maybe a current flow through the primary of this high frequency transformer, right? So only for that short time, the pulse is develop across the secondary of a transformer. Then again, there will be a rectifier to convert that AC into DC, then filter and so on. So this transformer is used in either in saturation or in a cutoff region, so that the transistor is not continuously on. So if transistor is not continuously on, the wastage of energy, that is maybe a power loss, is very low, and efficiency of this regulator is high. So this is one of the topic that some students have requested me to explain once again. So next one, these applications already we have seen in the last lecture. Uh, this is an interdisciplinary nature of a power electronics. So where the power electronics is used in a different branches or different field that is given here. So it is an interdisciplinary nature of power electronics. Power electronics using the system and control theory, signal processing, then simulation, uh, circuit theory, simulation. Okay, Surbhi, you can directly unmute and ask me what you want to ask. Okay. So electric machines, power system, electromagnetics, solid state physics, these are the different fields where the power electronics is used. Already we know that what is a power electronics. So these are the different field basically where the power electronics is used. That is just simply an introduction of these different fields in which power electronics is widely used. Uh, this is another figure that shows the interdisciplinary nature, electronics, devices, circuits, power statics, rotating power equipments, and continuous discrete control. This is another, maybe a broad sense of interdisciplinary nature that is shown here. Now, the introduction of these converters. This is the first point in your syllabus, that is comparison of power electronics and linear electronics, then interdisciplinary nature, and then introduction of power converters. So these are the power converters called AC to DC converter, called control rectifiers. Already you might have learned the rectifiers in first year or maybe in a second year. So these are again a rectifiers, but controlled rectifiers, so called AC to DC converters. Then DC to DC converters. Already we discussed about this, that we required variable DC in electric vehicle So from fixed DC to variable DC, we can get with the help of DC to DC converter, also called as a DC choppers. Then AC to AC converters, again we have discussed about this one in the last lecture. That is fridge stabilizer or TV stabilizer are the examples of AC to AC converters. This,
Regulator also.
yes,
Fan regulator. Example AC to AC.
okay. Regulators is not an example of AC to AC. Regulators,
Fan regu-
huh?
fan regulator.
Fan regulator. Okay, fan regulator basically is not a AC to AC converter. Fan regulator just used to control the speed of fan, nothing else. The name is given as a regulator, fan regulator, but it is not basically a AC to AC converter. What is basically AC to AC converter? The concept of AC to AC converter is not only uh, maybe to increase or decrease the AC voltage. That can be accomplished with the help of transformer even. But here AC to AC converter is basically one example I have given you, that is oven, right? And microwave oven basically, or maybe a cooking gas, that is maybe electric cooking, in which uh, maybe a line frequency is converted with a high frequency. Even tube light uh, choke, that is electronic choke. So which is the example of AC to AC converter. So supply voltage is AC 50 hertz, but the secondary or maybe output of that converter is a high frequency signal, right? So AC to AC, that's a bit discuss about the DC to DC, DC voltage, fixed DC to variable DC, but here fixed AC to variable AC, or fixed frequency to variable frequency. That is basically a AC converter. To fix a variable AC to fix AC, that is example of stabilizer. Then fix AC, fix AC to variable AC. That is also used in some applications where AC drive is controlled. And AC to AC, that is a fixed frequency to variable frequency. There are various applications of this fixed frequency to variable frequency. And the last one is a DC to AC converter. This is called inverter. DC to AC converters. So inverters, already we know that everyone maybe at home or in maybe in institute we are using inverters for backup. So this is a last converter that is called DC to AC converter. So just remember this, AC to DC is called controlled converters or controlled rectifiers. DC to AC converter called DC chopper. AC to AC converters called AC voltage regulators, or you can say stabilizers, and DC to AC converters called as a inverters. So these are the types of converters uh, that we have to learn in our consequent units, maybe in a third and fourth, fifth unit. These are basically a block diagram of converters, generalized block diagram, AC to DC, right? So, or maybe a DC to again AC and so on. So it is just a diagram given for your understanding what is a converters. Now, next topic of your first unit is power electronic devices. As we discussed in the first lecture, the devices uh, used in electronics that are normally used for switching purpose. So there are total 4 devices given in your first unit, that is thyristor or SCR, then MOSFET, then IGBT, I think, and tri. So these are the 4 devices given in your syllabus. So we'll see the classification of power devices. First one, uncontrolled turn on and off. So already you might have learned a diode. So similarly, a power diode is one of the power device which is uncontrolled device, but still it is used in a power circuits. So power diode, then control turn on, uncontrolled turn off. This is an example of SCR, in which on time you can control, but off is not in our hands to turn off the thyristor. Once it is on, it remains on. That's why it is called as a latching device. Then control turn on and off characteristics. Some devices are there in which you can control the on time and off time, or you can simply control the on and off both characteristics of devices. So examples are power transistor, BJT, MOSFET, GTO, gate turn off thyristor, and IGBT, insulated gate bipolar transistor. So these are the devices which are you can maybe control on and off characteristics of these devices. Thyristor, you can control only on characteristics. Once it turns on, it remains on till the voltage or anode current becomes zero. So you cannot control this device once it turns on. That's why it is called as a latching device. And these devices you can control the on characteristics as well as off characteristics. Then continuous gate signal requirement, normally for SCR, once SCR turns on, it remains on. After that, if you remove the gate voltage or gate current, it remains on. But these BJT or MOSFET or IGBT, it required a continuous gate signal. So this is a again a classification based on continuous gate signal. Then pulse gate requirement like SCR or a GTO, it required a pulse gate. Once you apply a particular pulse, that device turns on and it remains on. After that, if you remove the gate bias, uh, the device is remains on. Then bidirectional current capability triac. These triacs are used in a AC stabilizer or maybe AC to AC controller. Then unidirectional capability, SCR, GTO, BGT, MOSFET, IGBT, etc. So these classifications of power devices given on whatever the gate current or base current is required, and second one is that is on and off characteristics. So depends on that. Then see the history of these power devices. This history of these power devices. So okay, in a 1900 prehistory, basically mercury arc rectifier, vacuum tube rectifier, etc., thyratron, etc. These tubes are used for the conversion of the same thing or maybe as a switching purpose. Then in 1957's invention of thyristor, that is your ACRs, are uh, developed. So then in mid 1970s, the power diodes, application of fast switching, fully controlled semiconductor devices, basically BGTs, FETs, MOSFET, etc., are developed or maybe start to develop in mid 90s. Then a GTO, GTR, power MOSFET, thyristor, microprocessor that is developed in a second phase, that is in late 1980s. And then in third phase, IGBT, then power MOSFET, thyristor, DSP, etc. So this is basically history of a development of these power devices. So first power device as per your syllabus is power MOSFET. Students, before to see power MOSFET, you have to learn about the MOSFET, and I think you might have learned MOSFET in first year as well as in second year EDC. But still, we have to see how the MOSFET construct, maybe construction of MOSFET, and the working of MOSFET, even the drain and transfer characteristics of MOSFET, because there is a slight difference in a construction of simple MOSFET or you can say power MOSFET. In between these two devices, there is a small difference in a construction, but remaining the working, then characteristics, nature of characteristics, everything is same. Just the power handling capacity of our devices is more. So before to start the power MOSFET, you will see a MOSFET. What is a MOSFET? And before that, we have to see what is the difference between FAT, BJT. What is a FAT? What is a BJT? So we'll start with the transistor. Basically, transistor is a transfer the resistor. Transistor is a switching device, is amplifying device. It has mainly divided into two types, BGT and FAT. You can say bipolar transistor and unipolar transistor. Okay, so bipolar, it means the current conduction into the maybe device due to minority as well as majority charge carrier. You can say majority as well as minority charge carrier. And in unipolar devices like FAT, So FAT in which the current conduction through the device due to only majority charge carriers. That is the one difference. Then a BJT, basically BJT is a current control device. FAT is a voltage control device. Its name itself give the explanation, that is field effect transistor. So field, it means your voltage, field effect transistor. So FATs are voltage control device, BJTs are current control device. Okay. Then advantage of BJT, that is it has very high current gain, but at the same time the input impedance of BJT is low. And in FET, the FET has a very high input impedance, uh, but the current gain is low. So according to the applications, you can use BJT as well as FET in amplifier circuits. But normally MOSFETs are used as a switch in electronics circuits mostly. Uh, so these MOSFETs are also called as insulated gate field effect transistor. So this is about the introduction of MOSFET. These are the symbols of MOSFET, basically types of bipolar BJT and PN and PNP. Similarly, types of FET, which is maybe mainly categorized as a JFET and MOSFET. So junction field effect transistor and metal oxide semiconductor field effect transistor. So working of MOSFET and JFET is somewhat same. Even characteristics are same, but the construction is different. So these are the devices. It is called basically a N-channel MOSFET and P-channel MOSFET. So symbol, if you see here, these are the depletion type MOSFETs. That is second one. Gate, drain, source, and substrate. If you see, the channel is continuous in depletion type MOSFET, but in enhancement type MOSFET, the channel is discontinuous. So depletion type MOSFET is also called as a normally on MOSFET, and enhancement type MOSFET is called as a normally off MOSFET. So MOSFET, that is divided into two part: enhancement type normally off, depletion type normally on. Again, enhancement type is divided in two types, that is N channel and P channel. Similarly, depletion MOSFET is also divided into two types, N channel and P channel. Now we will see the working of this MOSFET, exactly how it works. Then we will discuss about that. Okay.
Let us discuss MOSFET.
Okay. This sound of this video is audible to you or not? Anyone unmute yourself and tell me the sound of this video is audible or not?
No, sir. No,
Huh?
sir.
No.
No.
Huh? Sound of this video is audible or not?
Not audible. Sir.
Okay. I'll first change the setting so that this sound is audible to you. Just a minute.
Let us discuss MOSFET in detail.
Now it is audible?
Yes, sir.
Okay. Just see this video. We'll understand the
MOSFET is an electronic device most widely used in ICs. It has three terminals named as source, drain, and gate. Construction of basic design of MOSFET is quite simple. Just take a block of P-type semiconductor. This block will be your base for MOSFET. We also call it as substrate, and the entire MOSFET we will fabricate on this base. Now, two portions on the same side of this P-type substrate are made highly doped with N-type impurity, as these are shown here in the figure. Source and drain terminals are brought out from these two N regions as shown. Now, the entire surface of the substrate is coated with a layer of silicon dioxide. Silicon dioxide will behave here as insulation. On this layer of silicon dioxide, a thin metallic plate is placed. This metallic plate will act as gate contact to the substrate. The gate terminal is brought out from this metallic plate. Hence, it is seen from the figure that gate contact is insulated from the substrate, but drain and source contacts are directly connected to respective N-type regions. This was the constructional feature of a MOSFET. Now we will come to the operational features of MOSFET. For that, we have to connect on DC voltage source between these two N-type regions. The N-type region connected with positive terminal of the source is called as drain, and the N region connected with negative terminal of the source is called as source. As soon as the drain and source are connected with DC voltage source, there will be two PN junctions formed. One is in between N-type drain and P-type base, and the other is in between P-type base and N-type source. As drain is connected with positive terminal of the source, the drain is in higher voltage than base. Hence, this PN junction is reverse biased. On the other hand, as source is connected with negative terminal of the battery, P-type base will be at higher potential than N-type source. Hence, this PN junction is forward biased. As between drain and source, there will be one reverse biased and one forward biased junction. There will be no significant current flowing from the drain to source, but a tiny current continues to flow due to minority carriers. We can say that virtually there is no continuous path or channel between drain and source. Now let us see what happens if one suitable positive voltage is applied at gate terminal of the device. In that case, due to attraction of positive potential of gate contact plate, negative free electrons, that is minority carriers in P-type base, will be accumulated towards a contact plate and form a channel of negative charge carriers even inside P-type semiconductor. This channel, due to higher concentration of free electrons, will behave as N-type semiconductor, although entire base is doped with P-type or trivalent impurity. It is obvious that the number of free electrons accumulated towards gate contact plate depends on the strength of positive potential given to the gate terminal. Hence, width of N channel depends on the voltage applied at gate terminal. More the applied voltage, greater the width of the channel, means greater the conductance between drain and source. Here we have seen that there is no direct connection between gate contact and substrate. Instead, these are insulated from each other. But due to electrostatic attraction, the conducting channel between drain and source is formed, and because of that, the channel is also called induced channel. And the device is called induced channel MOSFET. It is also clear that when there is no voltage applied to the gate of the device, there will be no current from drain to source, except negligible amount of saturation current due to minority carriers. But if the gate voltage is gradually increased by keeping fixed drain to source voltage after certain minimum applied gate voltage, drain to source current will start flowing. And this voltage is called threshold voltage. So, below threshold voltage, the device will behave as non-conducting or in off mode. And for gate
Okay. Uh, so this is all about the construction and working of MOSFET. The MOSFET explained that is a simple MOSFET, not a power MOSFET. Am I audible? Once again, tell me. Anyone unmute yourself and tell me. Am I audible?
Yes, sir.
Okay. So I will share this video with you so that you can easily understand and you can see the video after this lecture. So these MOSFETs, basically a construction of these MOSFETs is very simple. A P-type substrate, then a two N-type heavily doped N-type is a sandwich. Then there will be a SiO2 layer and a metal gate. Basically, metal oxide semiconductor filled transistor. So this gate is connected to the metal, this SiO2 layer, and these are the heavily doped, and this P is called as a lightly doped substrate, right? So what happens exactly when we apply, in depletion type MOSFET, if the gate voltage is zero, if gate voltage is zero, because basically this structure that is shown here is a enhancement type MOSFET. The construction of depletion MOSFET is not shown in this figure, only enhancement type MOSFET, and normally only enhancement type MOSFET is used as a switch. Depletion type MOSFETs are normally not used as a switch. So in this structure, if you see, there is a no continuous channel between these two N, right? So this channel is creates when you apply some voltage at the gate, and this voltage should be greater than threshold voltage. What is the threshold voltage? If you apply a gate voltage is equal to 1 volt, so what happens in this P-type substrate, there will be a minority charge carriers, which is maybe electrons, right? So these electrons get attracted towards this metal plate, right? Basically this metal, this SiO2 and this P is forms a capacitor. Basically the capacitor is formed, and in this capacitor, if you apply positive voltage at the gate of this capacitor or maybe a transistor, what happens? The electrons in this P region, that is a P substrate, that gets attracted. Now, which electrons? Basically a hello, hello, hello. Hello. Am I audible? Hello.